Okay guys, next section is quite short, but if you're not doing chemistry in particular, you'll find this a little bit challenging in terms of the letters. We're going to start thinking about what we did with the pressure, the volume and the temperature, and start relating it to the mathematics behind this. So this is the step in between. So we need to be able to describe mathematically with numbers what is about this gas. So I'll apologise now, there are lots and lots of very similar letters. So, going to start down at the bottom here, okay? There are two versions of the ideal gas equation. So, not these. This is the ideal gas law. The equation, or equation of state, sometimes called, is where we start bringing these together. So, that's this bit here. Then we're going to start bringing in Avogadro's, everyone's favourite constant from GCSE, I'm sure, Boltzmann constant, and the conversion between them. Okay, so really this section is all about conversion. Now, because of that, we have mass in different ways, so we have different m's, we have different numbers of particles. It all gets a little bit complicated. But if we go back to GCSE, and I will apologise for the chemists who probably use slightly different lettering, so MR and things like that, we're just going to keep it simple. So what we're after is the number of moles. We all remember about moles, don't we? It's a certain number, it's on your data sheet, and it's 6 times 10 to the 23. So in one lump of material, one lump of gas, we have 600,000 million molecules. Okay, they could be single atoms, monatomic, they could be pairs, diatomic, or they could be bigger molecules. It doesn't matter, it's the number of molecules that are in there. So if I talk about molecules, I could also be talking about lone atoms bouncing around. Okay, it doesn't matter. Not for the model anyway. So the number of moles, N, is literally the total mass of the gas, which is in this case going to be M with a little subscript G, and we are going to divide it by an M, okay, where this is our molar mass. So what that is a capital M, okay, so notice that's capital, okay, hard to tell possibly with mine, but that's a little n, and you'll see why in a second. Okay, so this is, I should say still, mass in grams and mass in grams, or kilograms and kilograms. It does not matter because it's the ratio of how many lumps of gas you have. So if you think of say an Avogadro 1 mole of gas, then you may have learned that that's around about 22 litres of air at standard temperature and pressure, but it doesn't matter. Okay, stick away from that. It's just how many total particles divided by how many you've got in a single mole. Okay, a little bit of warning, so a little bit there, just have a read through just to make it a little bit easier. But generally they tend to make the questions quite simple so you don't get confused. Now, what Avogadro cleverly did early on is he suggested it was to do with molecules, so that's where he came up with this number, and so we can look at n in a different way, same little n, but it is the total number of particles divided by the number of particles in a mole. Okay, so this one, as I said there, molecules, let's say molecules, in 1 mole. Okay, so that will give you the same thing. Total number of particles gives us the total mass. Total number of particles in a mole gives us the mass of a mole. So it's just really about the particles inside. And again, constant is there, it's on the data books, you can think of it in that way. So if I wanted to rearrange it around, what that means is I can think of the amount of gas we've got. So if we want gas, so I'm going to call the mass of the gas, I'll put gas just to make it really clear, then that is going to be the number of moles multiplied by the mass of each mole, nm. Okay. But from what we've just said, little n, rearrange that, is actually going to be the ratio of the two things. So I could put that in as capital N over Avogadro's number, okay, multiplied by mass, big mass. But from my first equation, again, make that really clear, that's a capital, but m equals little m, okay, if I divide by Avogadro. So if I take the mass of a molecule, sorry, a mass of a mole of molecules and divide by the number of molecules, I'll get the mass of individual particles, okay? So what that means is that actually the mass of gas, mass of gas can also equal capital N, okay, multiplied by little m. You just merge those two together, okay, or replace that. If you're not sure, let me just clarify that. That's across the top, okay? So I can think of the mass of gas in two ways. A small number of moles times by a mole of mass, or a large number of particles multiplied by the mass of the particles. Okay, so we can think at a molar level, or we can think of an individual particle level, okay, the molecule level. Notice the layout of the letters. So n, little n, is a small number. That's a much, much bigger number. Okay, millions and millions and millions and millions, Avogadro times bigger. That is a large mass, because that's a bag of gas. 1 mole is a bag, whereas that's a small mass, so we use a small m. Okay, so the small letters, the lowercase letters, represent small numbers, and the large letters represent large numbers, large mass or large number of particles. Okay, but they're both saying the same thing. So we can consider gases and how they behave at two levels: chemistry level, shall we say, and individual particle level, which is where we start thinking about where these equations came from. So let's just have a think about what's going on with that. Let me just pull that. Yeah. So if we're thinking about the individual gases at low temperatures, say gases form vapors. Okay, so you can actually then squash them and they become liquid. If you still steer well away from that, I mean, we're talking minus 200 degrees. So if we're in normal day temperatures, all gases will behave pretty ideally. There's almost no potential energy in the bonding. There's no bonding. So from that, we can come up with a letter to represent that ratio. So where we were the other day, we can have PV over T equals R. Okay, now if we then go up and say, well, that's for one bag of gas, if we keep those but actually then start bringing in more bags, more moles of gas, then what we're just doing is we're ending up with multiplying that and scaling that up. So pressure and volume will be bigger, okay, but we're just sticking in small n for small number of moles. Okay, if that is 1, you get this equation. If that is 2, then the pressure volume will be twice as big. Maybe the pressure will be twice as big, or the volume will be twice as big. It doesn't matter, or both. But yeah, those are proportional to the number of moles. And so what that does is we can rearrange that to make it flat, and we have nRT. So that is the equation of state for gases, for ideal gases, and we can use that when we're talking about large quantities. In other words, if they say moles, then you can use the molar gas constant. This is in the data sheet, the equation is in the data sheet. Okay, so that's useful. However, not much useful for where we're going. However, while I remember, let's just go back. where we were actually in last lesson in your notes. Just please notice that this is not in the data sheet. Okay, so please be wary, you'll need to remember that, but obviously you've got the equation there, you've got the P, the V and the T, you just need to say that's some constant, so you don't need to know what N and R is to do all the calculations with gas. Okay. However, when we're getting to an individual level, we do, so there's a little bit of sneakiness going on, and the sneakiness is actually Boltzmann coming along and making that conversion. So what we'll do, again, just to kind of go through some steps, so PV equals nRT, little n, number of moles, molar gas constant. Well, from our conversion, we could actually write that as, total number of particles over Avogadro's constant, and R and T again. Okay, so what I can do is I can translate that ever so slightly, and we can say PV, it's just cleaning it up a little bit, we can have a large N, we can have the temperature still, and then we can have a value of constant divided by a constant to give a more convenient constant. So this is actually to again scale, to scale to individual particle level. Particles. Okay, so we can start doing the idea of these and the RMS speed of them and stuff like that. So he took the idea that because they're both constants, we can make that a lot simpler, which of course we can, and so we have a shall we say a physics version of the same equation, and he realized that the ratio will always give that same answer because they're both ratios, not genius, but he represented that as a way of thinking about the internal energy per molecule, okay, rather than per lump of gas. So he gave that lowercase k, the Boltzmann constant, as that ratio that we've just done. So largest number over very large number. So what you end up with is k, which is a very small number. Okay. Now, interestingly, that is how much smaller? Well, it's Avogadro times smaller than the other one. The other one, R, has a value of 8.31. This has 1.38. Nice and symmetrical, but it's times 10 to the minus 23, so it's really, really small. So we have two equivalent gas equations, and this really shows up why you need to know and make clear what your letters are. Okay, small number, small letter, lowercase. Big number, big letter. Small number of moles, big number of molecules. Yeah, so it's all about that size. So this is for a mass of gas. Should we say a large mass of gas, a large number of particles? Whereas this is for particles. And both of them are in the data book. This is really important for individual particle level, particle accelerators, etc, etc, etc. But this tends to be quite a useful everyday stuff, which again is why chemists tend to use it, because they're not dealing with the individual particles. They have millions and millions of them. Okay, so I'll leave it with that. Have a think about it. It's all about trying to make clear in your head. It's very, very, very easy to get confused between the different M's, the different N's, etc. And the crucial link is Avogadro constant. All of them are ratio. So you divide one constant by another, you get that. You divide one mass by another, you get that. You divide one number of particles by the number of moles, you get that, etc, etc, etc. So they're all, that's the multiplying ratio factor that comes in with all things gaseous. Okay, we'll leave it there. Thanks, guys.